Math 2415, section 10.5, equations of lines and planes. This video is meant to pick up where we left off in class on Tuesday, September 3rd, when we had just introduced how to write the equation of a line in space if we know two things about that line. If we know it contains a certain point, which we generically represent as x naught, y naught, and z naught, and is parallel to some given vector, which we're calling vector v, and in component form, we're representing as a comma b comma c. But if we have a line that contains that point and is parallel to that vector, then the equation of the line in vector form is vector r equals t times vector v plus r naught, vector r naught, where vector r naught is the vector whose components are x naught, y naught, z naught. In other words, if we have a point in space, we'll just put it out here somewhere, x naught, y naught, z naught, then r naught is the vector, or one location of r naught is the vector whose initial point is at the origin and whose terminal point is at that given point. Also, the vector r is like our variable vector. It's the variable that contains generic coordinates x, y, and z. Because if we are going through a certain point and we're parallel to a certain vector, for example, let's say we're parallel to this vector v, then the equation of the line that we're looking for is, or the line whose equation we're looking for is this one, that is parallel to vector v but goes through this point. And what the vector r represents is if you pick a generic point, x, y, z on this line, then the vector r can be thought of as the vector connecting the origin to that generic point on the line. I'm not going to reinvent why the equation is this, but the gist of it was that the vector, well, I'm sort of not going to reinvent it, but the vector connecting r naught to r, or rather the terminal point of r naught to the terminal point of r, had to be the vector r minus r naught to complete the vector addition problem. That, coupled with the fact that if two vectors are parallel, one is a scalar multiple of the other. So if we subtract the r naught back over here, we have r minus r naught is equal to some scalar multiple of the parallel vector v. And then we just move the r naught over. For example, let's say that we have a line passing through the point 5, negative 2, 7, and is parallel to the vector negative 2, 4, 3. And we wanted to write the equation of this line in vector form. Then the equation would be r is equal to t times the vector negative 2, 4, 3. That's our direction vector, if you will, tells us the direction of the line, plus the vector being represented by the given point, which in this case would be the vector 5, negative 2, 7. Again, okay, that was a random collection of words. If we change out the vector r with what it's representing, a generic vector x, y, z, or equivalently a generic point x, y, z, again, remember the very subtle distinction between saying x, y, z in parentheses versus x, y, z in vector brackets, if you will. In parentheses, it means the single point space. In the vector brackets, it means the vector that connects the origin to that point in space. If we replace vector r with its component form x, y, and z, then we get that the vector x, y, z is equal to t times the vector negative 2, 4, 3 plus the vector 5, negative 2, 7. This would be the equation in vector form. We didn't do an example last time, but it's really not that difficult to set up once you have a point and a parallel vector. Without doing an example, if you're told that a line goes through 2 points, then we don't have the right ingredients to build this equation, because we would have 2 points and we only need 1, but we wouldn't have a parallel vector. It would be easy to find the parallel vector. We would just have to subtract the corresponding coordinates of the 2 points. In either order, and that would give us a vector that goes through those 2 points, and therefore the line going through the 2 points would indeed be parallel to that vector. Let me say it again. If you have a question that says, what is the equation of the line that goes through these 2 points, subtract the points' corresponding coordinates to come up with the parallel vector, use either of those 2 points as the given point, and then you can build your equation of your line. As you can tell, because you have some choices to make, the equation in vector form of a line is not unique. It depends upon the point that you use and the parallel vector that you use. I want to quickly show you the other 2 forms because they're fairly intuitive. The second form is called, it's not component form. It involves the components, but it's called parametric form. At the end of Calculus 2, you should have discussed parametric equations. Unfortunately, sometimes that topic gets sacrificed at the expense of time, meaning you run out of time. But parametric form is where you describe the equation of the line not as one vector equation, but you look at it at the component level. In other words, you try to figure out what each component has to equal on the left by equating it to the components on the right. What I'm about to write here is not parametric form, I'm leading up to it. Let me go back up to this previous one and put a box around what I would think would be a good final answer for vector form. But for parametric form, basically you want to ask the question, what is x equals, what is y equal, and what is z equal? Well, in order to do that, we need to combine the expression on the right side of the equal sign into a single vector in component form, and it wouldn't be that hard to do. In fact, I'm going to do it in one move because this is Calculus 3 and you should be able to handle little baby algebra steps. We can combine the right side into a single vector by distributing the scalar across the components, so each of these components would pick up a t, and then adding corresponding components. So put a t here and add it to its component over there. In the x component, we would have negative 2t plus 5. In the y component, we would have 4t plus negative 2, so minus 2. And in the z component, we would have 3t plus 7. Now, this isn't parametric form. This is still technically vector form because I have one vector is equal to another. Parametric form is where you just explicitly state what each component is equal to. In this case, x is equal to negative 2t plus 5, y is equal to 4t minus 2, and z is equal to 3t plus 7. And I neglected to mention up here that the value of t can be any real number. Basically, the t says how many of these vectors do you want to go in this direction from the given point. For example, if t was 2, it's basically saying take 2 copies of these from the point and it takes you to another point. Or with a negative scalar like negative 1/2, you would take half of this but in the other opposite direction from this point, go half that way along the line, and there's another point. So that's all the t is. It's any real number you want, but what it measures is how many of the parallel vector do you go, either in the positive direction or the negative direction, depending as to whether t is positive or negative. This collection of 3 equations is called parametric form, and these are your parametric equations. T is the parameter, and essentially t can be any real number, so we can say t is an element of the interval negative infinity to infinity. So choose a value for t, substitute it, and you calculate a point on the line. As far as symmetric form is an offshoot of parametric form, and I'll be honest, I really don't have much use for it. It's pretty, it's neat, and I'm sure there's a good use for it, but it's just one of those things that I look at and go, oh, that's neat from a theoretical perspective, but from a physics and engineering perspective, and you guys know I'm neither a physicist nor engineer, I'm not sure the benefit of it. Perhaps a physicist or engineer could elaborate on that. But symmetric form is an offshoot of parametric form where basically you eliminate the parameter. The way you can eliminate the parameter is to solve each one of these parametric equations for t. Well, let's do that first. If we solve everything for t, the first equation will become x minus 5 over negative 2 is equal to t. The second equation would become y plus 2 over 4 is equal to t. And the third equation would become z minus 7 over 3 is equal to t. Now this technically is still in parametric form because I have 3 parametric equations. But what symmetric form is where you set all 3 of these equal to each other because they all equal t. So you would say x minus 5 over negative 2 is equal to y plus 2 over 4, which at the same time, z minus 7 is equal to z minus 7 over 3. This compound equation, if you will, it's really 2 or 3 equations depending upon your perspective. 2 equations are the first 2 are equal and the last 2 are equal, but the third equation that's implied is that the first and the third are equal. But this is called symmetric form. Now, you can probably figure out that you can build any of these 3 forms instantly if you have the same information. In other words, if you have a point that a line goes through and a parallel vector, then you can set up any of these forms, and vice versa. From these forms, you can extract a point that the line goes through and a vector that the line is parallel to. So in general, if the line contains the point x naught, y naught, z naught, and is parallel to ABC, then we can write all 3 forms directly. Vector form would be xyz is equal to t times ABC plus x naught, y naught, z naught. So there's this generic setup for vector form. For parametric form, remember, parametric form is where you basically condense the right side of vector form into a single vector and then just equate components. Parametric form would be x equals, we'll say at, because t being the variable actually shows up after the constant. So at plus x naught, y is equal to bt plus y naught, and z is equal to ct plus z naught. And then symmetric form, and by the way, I forgot to mention that symmetric form is not always an option. Symmetric form is not always an option because by its own design it has denominators, and denominators can't be 0. If you think about it, these denominators all came from the vector. And so symmetric form only works if none of the parallel vector's components are 0. Another way of saying that is symmetric form works only if ABC is not equal to 0. Think about what that means. The only way a product can equal 0 is if one or more of its factors is 0. So symmetric form is only an option when the product of the parallel vector's components is not 0. In other words, when the parallel vector has no 0 component, then symmetric form would be x minus the x coordinate of the given point over the x component of the parallel vector equals y minus the y coordinate of the given point divided by the y component of the parallel vector, which are both equal to z minus z naught, so z minus the z coordinate of the given point divided by c divided by the z component of the parallel vector. So in your homework for 10.5, when I assign it, the majority, not the majority, but pretty much all of the questions about lines involve one or possibly more of these forms of the equation of a line.